The room is dim, lit only by a soft console glow, and a thin ribbon of radio hiss slides through the speakers. That faint noise is older than you think, stretched across light years before it reaches your ear. If the galaxy is crowded with life, this sound should be crowded too, so why does it feel empty? You sit with the hiss for a moment. It never quite stops. Outside the control room window, a dish the size of a football field turns by a fraction of a degree. Motors hum low and steady. The movement is slow enough to miss unless you watch the rim against a distant ridge. We built these machines because radio waves cross space with little effort. Dust cannot block them. Gas barely slows them. If anyone is speaking across the stars, radio is the first place you would listen. The puzzle has a name now, the Fermi Paradox. It comes from a simple question asked in the mid-20th century during a casual lunch among physicists. The galaxy is vast and old. Stars have been forming for more than 10 billion years. Even slow expansion, measured in tiny fractions of light speed, could spread a civilization across the Milky Way in a few million years. That is a blink compared to the galaxy's age. So where is everybody? It sounds dramatic, but the math is calm. The Milky Way holds roughly 100 to 400 billion stars, based on star counts and models of stellar mass distribution. We measure this by mapping star motions and light output, then fitting that to gravitational models. There is uncertainty in the exact number because dust hides parts of the disk. Still, even the lower bound is immense. You feel the scale settle in. In the past 3 decades, major space missions and ground observatories have confirmed that planets are common. We know this because of 2 main methods. First, the transit method watches a star's light dip when a planet passes in front of it. Second, the radial velocity method measures tiny shifts in a star's spectrum as a planet's gravity tugs it back and forth. These techniques have revealed thousands of confirmed exoplanets, and statistical studies suggest most stars host at least one planet. The consequence is simple. Worlds are not rare. Some of those planets sit in what we call the habitable zone. Think of it like the warm band around a campfire where water can stay liquid. Precisely. It is the range of orbital distances where a planet with the right atmosphere could support surface liquid water. Liquid water matters because, on Earth, every known form of life depends on it. The consequence is not that life must exist there, only that the basic chemistry would not be instantly hostile. We can measure this band using stellar brightness and orbital mechanics. There are margins of error because atmospheres vary. A thick carbon dioxide layer can trap heat. A thin atmosphere can lose it. Still, many stars appear to host planets within this zone. By conservative estimates, there may be billions of potentially habitable planets in our galaxy alone. And yet, the radio hiss continues. A red light blinks on a rack of receivers. Cooling fans push air through metal grids. The dish outside shifts again, aligning with a narrow patch of sky near the plane of the Milky Way. We are not guessing blindly. SETI, the search for extraterrestrial intelligence, scans specific frequency ranges that might carry artificial signals. One famous band sits near the emission line of neutral hydrogen, around 1400 MHz. Hydrogen is the most common element in the universe. Any technically aware civilization would know its spectral signature. The logic is almost polite. Meet at the obvious place. How do we know what counts as artificial? Natural radio sources tend to produce broad, noisy spectra. Pulsars pulse with clock-like precision, but their signals spread across frequencies in characteristic ways. An engineered signal, in contrast, might be narrowband. It could concentrate power into a very tight frequency range, because that is energy efficient and easy to detect against background noise. Instruments search for such narrow spikes. They filter out known satellites and terrestrial interference. They repeat observations to confirm that a signal tracks with the sky instead of Earth's rotation. There are false alarms. A microwave oven once fooled a detector when someone opened the door mid-cycle. That taught us to cross-check and verify. As of 2026, no confirmed extraterrestrial signal has passed these tests. This is Tier 1 territory. The silence is real within the limits of our searches, but those limits matter. Our surveys cover slices of the sky, slices of frequency, and slices of time. Imagine dipping a glass into the ocean and finding no fish. It does not prove the sea is empty, it defines the volume you sampled. That constraint changes the tone. A truck rolls down a distant road beyond the observatory fence. Headlights sweep across the dish for a second, then fade. The sky above is clear and cold. When you look up, the Milky Way forms a pale river. Each point of light is a sun. Many have planets. Some planets sit in temperate orbits. Chemistry is not rare. Energy is not rare. So why no sign of industry, of artifacts, of probes? The paradox sharpens when you consider time. Our species has used radio for just over a century. That is a whisper compared to the age of Earth, which is about 4.5 billion years, dated through radiometric analysis of rocks and meteorites. Civilizations elsewhere, if they exist, could be millions of years older than us. Even if intelligent life is rare, the galaxy has had ample time to try many times. Unless something blocks the path. That possibility is called the Great Filter. It is not a single event we have measured. It is a placeholder for one or more steps in the chain from simple chemistry to spacefaring civilization that are extremely unlikely. The analogy is a series of doors in a long hallway. Life must pass each door to move forward. If one door is almost always locked, few make it through. The consequence is stark, the silence might be selection. But before we jump there, we have to examine a simpler explanation. Maybe advanced civilizations do not broadcast loudly. Maybe radio is a short phase. On Earth, we are already shifting toward fiber optics and tightly beamed transmissions. Our radio leakage into space may fade within centuries. If that pattern is common, the window to detect a society by stray radio could be brief. We can estimate this window by modeling technological transitions. The uncertainty is wide because we have one data pointus. That makes this tier 2. It is plausible, but not settled. If true, it implies that civilizations could overlap in time only rarely, even if many arise. The dish outside pauses, it waits. There is another angle. Even slow interstellar travel, at perhaps 10% of light speed, would allow a civilization to spread across the galaxy in tens of millions of years. That number comes from a simple division. The Milky Way spans about 100,000 light-years. Hopping between nearby stars in stages reduces the required travel per leg. Robotic probes could do the work. Self-replicating machines, in theory, could accelerate expansion. We have not observed such probes in our solar system. Extensive surveys of near-Earth space and planetary surfaces show no clear alien artifacts. That is Tier 1 within observational limits. Of course, absence of evidence is not evidence of absence. Small objects could hide. Still, nothing obvious stands out. A quiet thought settles in. Maybe the solution is not louder signals, but quieter civilizations. The Fermi Paradox is not a single claim. It is a tension between numbers and silence. Large numbers of stars, many planets, billions of years, no confirmed contact. To move forward, we need to measure each term carefully. How common is life? How often does intelligence arise? How long do civilizations last? How detectable are they? Each term can shrink or expand the answer. Steam curls from a paper cup on the console. The room smells faintly of warm circuits and coffee. You lean closer to the hiss, as if it might resolve into a pattern. It does not. But the silence itself is data. It sets upper limits. It narrows possibilities. It forces precision. And it hints at something deeper. What if the reason we hear nothing is not because no one is there, but because the kind of civilization that survives long enough to matter becomes almost impossible to notice? If that is true, the solution to the paradox would not be a signal waiting to be found. It would be a constraint hidden in plain sight, shaping every advanced society in the same quiet way. Outside the dome, wind moves through dry grass, and the dish holds steady against the stars. The galaxy above you is not just wide, it is old beyond daily sense. If even one society learned to cross that distance long ago, their traces should be common by now. So why does the sky still look untouched? A red LED blinks once, the hiss continues. To feel the paradox, you have to feel the scale. The Milky Way is about 100,000 light-years across, measured by mapping star positions and motions in infrared surveys that cut through dust. A light year is the distance light travels in 1 year, about 6 trillion miles. The consequence is simple. Even light needs 100,000 years to cross our galaxy end to end. Now consider time. Stars like our Sun have lifetimes of about 10 billion years, estimated from stellar models that match mass, brightness, and nuclear fusion rates. Earth formed about 4.5 billion years ago, dated by radiometric clocks in ancient rocks. Intelligent radio use here is barely a century old. In cosmic terms, that is less than a blink. You are early, or you are not. If a civilization emerged even 1 million years before us, that head start would dwarf our entire technological age. 1 million years is 100,000 times longer than our radio history, and the galaxy has had billions of years to produce such head starts. This is not hype, it is arithmetic. The tension tightens. Suppose travel between stars is slow by our standards. Imagine ships cruising at 10% of light speed. That speed is far beyond current human capability, but it obeys known physics. At that pace, crossing 10 light years takes about 100 years, hopping from star to star in stages. A wave of exploration could move outward over millions of years. Even if expansion pauses between launches, models show that a civilization could spread across the Milky Way in tens of millions of years. Compared to 10 billion years of galactic history, tens of millions is small. This estimate comes from simple diffusion models and percolation simulations. They assume finite speeds and realistic star spacing. The uncertainty lies in motivation and resources, not geometry. So the question sharpens. Where are the footprints? A cooling pump hums behind you, pushing liquid nitrogen through receiver lines. The instrument does not care about philosophy. It collects photons and logs timestamps. When we talk about footprints, we mean detectable changes in matter or energy, mining scars on asteroids, artificial light on planetary night sides, excess infrared heat from large structures. These are technosignatures. We have looked for some of them. Infrared sky surveys measure waste heat. The logic is rooted in thermodynamics. Any advanced industry that uses large amounts of energy must release heat, because no process is perfectly efficient. Waste heat radiates mostly in the infrared. Space telescopes map this glow across galaxies and star systems. So far, no clear, galaxy-spanning engineering projects have been confirmed. This is Tier 2. Surveys have limits in sensitivity and resolution. Dust can mimic excess infrared. Natural star formation can also glow brightly. We cross-check by comparing spectral shapes and spatial patterns. The absence of obvious, large-scale anomalies suggests that galaxy-wide civilizations are rare, or they manage energy in ways that blend with natural backgrounds. A truck shifts gears on the distant road. Sound fades again. There is another angle to scale. The galaxy is not uniform. It has a thin disk, a central bulge, and spiral arms rich in gas. Star formation rates have changed over time. Billions of years ago, the rate was higher. That means more stars, and likely more planets, formed earlier. If life tracks star formation, then many potentially habitable worlds could be older than Earth. Studies of stellar ages using spectroscopy and motion data suggest that a large fraction of Sun-like stars are older than our Sun. That implies that if life arises readily, some biospheres had a head start of billions of years. This is Tier 2 because age estimates have uncertainties in stellar modelling. Still, the trend holds across large samples. Older worlds, more time. Now add chemistry. Elements heavier than hydrogen and helium are forged in stars and spread by supernova explosions. Planets require these heavier elements. Observations show that metallicity, the fraction of heavy elements, increased over cosmic time. Early in the universe, there were fewer building blocks for rocky planets. That could delay the emergence of habitable worlds. This matters. If the peak era for Earth-like planets came after the earlier stars, then the window for advanced life might cluster later than you expect. Measurements from large exoplanet surveys suggest that small rocky planets form around a wide range of metallicities, but very low metallicity environments may produce fewer of them. The uncertainty is active research. So maybe we are not late. Maybe we are near the front edge. Yet even if Earth is not especially early, the numbers remain large. Billions of stars, billions of years. Even rare events can occur many times under those conditions. If intelligent life arises once in a billion habitable worlds, the galaxy could still host several. The paradox is not that life must be everywhere. It is that even a modest rate seems to predict visible consequences. A monitor displays a sky map dotted with scan paths. Each line marks hours of listening. When we estimate detectability, we must consider signal strength. A powerful beacon aimed at us would be easy to spot. Random leakage, like our own television broadcasts, fades quickly with distance. The strength drops with the square of distance, double the distance, and the signal spreads over 4 times the area. That law is measured every day in physics labs. It is tier 1. It means that unless a civilization beams energy deliberately, detection across thousands of light years is hard. This constraint softens the paradox. Silence may reflect geometry, but geometry does not erase time. Over millions of years, a society could place probes in many systems. Even slow robotic craft travelling at a few % of light speed could reach nearby stars in centuries. The nearest star system is just over 4 light-years away. On cosmic timescales, that is next door. We have surveyed parts of our solar system with high resolution. Orbiters have mapped Mars, the Moon, and asteroids. We see no clear alien machines. That does not prove none exist. Small, dormant probes could hide in shadows or distant orbits. Still, no unambiguous artifacts have appeared. The night feels wider now. You lean back in the chair. The scale problem is not emotional. It is structural. The size and age of the galaxy create expectations. If technological life is common and expansion is typical, the Milky Way should show signs. If it does not, then at least one assumption in that chain is wrong. Either life is rare, or intelligence is rare, or survival is rare, or visibility is rare. We cannot choose based on preference. We have to test each link with data. That means counting planets, measuring atmospheres, modelling evolution, and searching for signals in ways that reduce blind spots. The dish outside begins a slow new sweep. A faint creak echoes through the structure as it moves. You realise that the paradox is not a claim about aliens. It is a mirror held up to our own future. If the galaxy is quiet, it may be because most civilizations pass through a brief, bright phase and then fade, or turn inward, or change form. The wind brushes the dome again, and the scale of it all presses close. If billions of years and billions of worlds have not filled the sky with noise, then the solution will not be simple abundance. It will hinge on a constraint powerful enough to shape the destiny of nearly every advanced society in the same way. A thin line crawls across the monitor as fresh data streams in, each point a star with a story. The equation we use to frame that story fits on one line, yet it carries the weight of a galaxy. If the numbers lean high, the sky should hum with life. If they lean low, the silence makes sense. The room stays quiet. We start with the terms. The Drake equation is not a law of nature. It is a bookkeeping tool. Think of it like a lens that breaks a big question into smaller, countable pieces. Precisely. It multiplies factors such as star formation rate, fraction of stars with planets, number of habitable planets per system, fraction that develop life, fraction that develop intelligence, fraction that use detectable technology, and the average lifetime of such civilizations. The consequence is practical. Each term can be measured or constrained. Begin with star formation. Observations of hydrogen clouds and young stellar clusters show that the Milky Way forms roughly 1 to 3 new stars per year. As of current estimates, we infer this by measuring ultraviolet light from young stars and radio emissions from star-forming regions. There is uncertainty because dust absorbs light and models vary. Still, the range is narrow enough for our purpose. Next, the fraction of stars with planets. Exoplanet surveys using the transit and radial velocity methods suggest that most stars host planets. Statistical corrections account for detection bias, since we are more likely to see large planets close to their stars, after adjusting for that bias. Analyses indicate that planets are common, likely around the majority of stars. That term is strong, worlds are plentiful. Now consider how many of those worlds might be temperate. Using data from space telescopes that monitored hundreds of thousands of stars, Astronomers estimate that a significant fraction of Sun-like stars host Earth-sized planets in their habitable zones. The exact percentage varies by stellar type and model assumptions. For Sun-like stars, estimates often fall in the range of a few to perhaps 20%. This is Tier 2. The uncertainty comes from small sample sizes and assumptions about planetary atmospheres. Yet even conservative values imply millions of potentially temperate worlds in our galaxy. The next step is harder: life itself. We have one confirmed example of life emerging from chemistry. Earth shows evidence of life dating back at least 3.5 billion years. Based on isotopic signatures in ancient rocks and fossilized microbial structures, the early appearance of life after Earth cooled suggests that, given the right conditions, life might arise relatively quickly, but we cannot yet measure how often that happens elsewhere. This term remains Tier 3. We must label it uncertain. A testable prediction would be the detection of biosignature gases, such as oxygen paired with methane, in the atmospheres of exoplanets. Future telescopes capable of high-resolution spectroscopy could confirm or falsify the frequency of life-bearing worlds. You feel the uncertainty widen. Even if life is common, intelligence may not be on Earth. Complex multicellular life appeared hundreds of millions of years ago, yet technological intelligence arose only once. As far as we know, evolution does not have a fixed direction. It responds to local pressures. Some argue that intelligence offers survival advantages. Others note that for most of Earth's history, simple organisms dominated. We cannot assign a confident probability here. This is Tier 3 as well. A way to test it indirectly would be to detect multiple independent technosignatures across the galaxy. If they are rare or absent, that constrains the fraction of life that becomes technological. A soft click echoes as the receiver switches bands. The equation continues. The fraction of intelligent species that develop detectable technology is shaped by culture and physics. On Earth, radio and radar emerged within a century of industrialization. That suggests that technological pathways can produce detectable signals quickly once certain energy thresholds are crossed. However, societies might choose not to broadcast, or may transition to less detectable communication methods. This term is Tier 2. We have one data point but clear physical principles. Any society using large-scale energy will interact with electromagnetic fields and thermodynamics in measurable ways. Whether those interactions are visible at interstellar distances depends on scale and intent. Then comes the lifetime term. This one carries weight. If a civilization's detectable phase lasts only a few hundred years, overlap between societies becomes rare. If it lasts millions of years, the galaxy should show signs. On Earth, industrial civilization is only a few centuries old. We do not know how long it will persist. Risks include environmental strain, resource limits, and self-inflicted catastrophe. There are also stabilizing factors such as technological adaptation and cooperative systems. This term is deeply uncertain. Tier 3. A testable prediction could be statistical patterns in exoplanet atmospheres showing industrial pollutants. If we detect none across many suitable worlds, that may imply short lifetimes or low frequencies. You watch the numbers multiply in your mind. Even modest values can produce large results if the lifetime term is long. Conversely, even generous assumptions about life and intelligence can yield near zero if detectable lifetimes are brief. The equation does not solve the paradox. It clarifies where ignorance lives. A distant door shuts in the hallway. The air settles again. There is a subtle shift here. Early versions of the equation leaned on speculation. Today, several terms are grounded in measurement. We know stars form steadily. We know planets are common. We know habitable zones exist. The unknowns have moved deeper into biology and sociology. That changes the center of gravity. The paradox now hinges less on astronomy and more on survival and detectability. If life arises often but rarely becomes intelligent, silence follows. If intelligence arises but collapses quickly, silence follows. If advanced societies minimize outward energy waste, silence follows. We can narrow some paths. For example, large-scale colonization should leave physical traces, if even a small fraction of civilization spread widely and last long. The galaxy could show clusters of engineered systems. Infrared surveys and searches for unusual stellar light curves constrain such scenarios. So far, nothing definitive appears. Constraint after constraint. A faint reflection of the Milky Way arcs across the control room glass. You realize that the equation is not about aliens in abstract. It is about thresholds, energy thresholds, complexity thresholds, stability thresholds. Each term is a filter. Pass enough filters, and a society becomes visible. Fail one, and the sky remains dark. As of 2026, the measured terms point to abundance in the early steps and deep uncertainty in the later ones. That narrows the mystery. The silence likely hides in biology, behavior, or longevity rather than in star formation or planet scarcity. The monitor flickers as another scan completes. Data fills the grid. If the solution to the Fermi Paradox exists, it will not be a single dramatic revelation. It will emerge from tightening bounds on these terms until only a narrow range remains. And when that range becomes small enough, it will force a conclusion about our place in the galaxy that is harder to ignore than the hiss in the speakers. The dish tilts a fraction of a degree, and the faint hum of its motors blends with the night air. Somewhere in that slice of sky, a star rises over an unseen horizon. If anyone there is transmitting, the signal is crossing space right now. The question is not only whether they speak, but whether we are listening the right way. A soft relay clicks. The scan begins again. Radio waves are invisible ripples in electric and magnetic fields. Think of them as long ocean swells rolling through empty space. Precisely. They are electromagnetic radiation with wavelengths longer than visible light. The consequence is practical. They travel vast distances with little absorption, especially through the thin gas between stars. That is why early searches focused on radio. Large dishes collect faint waves and funnel them to cooled receivers. Cooling reduces thermal noise inside the instrument. Every receiver has its own hiss caused by random motion of electrons. Lower the temperature, and that hiss drops. We measure this noise in units called Kelvin, tied to absolute temperature. A lower system temperature means better sensitivity. Sensitivity is everything. When a telescope scans the sky, it samples narrow frequency channels. Natural sources like quasars and nebulae emit across wide bands. An artificial transmitter, designed for efficiency, would likely compress power into a very narrow band. That produces a spike in one channel. Software flags such spikes and checks whether they drift in frequency as the Earth rotates and orbits. Drift matters. It proves the source is distant. If a signal tracks with Earth's motion in a way that matches celestial coordinates, it becomes interesting. If it stays fixed relative to local time, it is probably terrestrial interference. Satellites, aircraft, even faulty electronics can mimic narrowband signals. That is why candidate detections are reobserved and cross-checked with other facilities when possible. This process has produced false alarms before. A strong signal once appeared and vanished, never repeating. Without repetition, confirmation is impossible. The lesson was caution. Claims require persistence and independent verification. As of 2026, no narrowband signal has survived these filters. That does not mean no one transmits. It defines our search volume. Imagine scanning a beach with a flashlight. You see what falls inside the beam, and during the time you are looking, SETI surveys cover parts of the sky and parts of the spectrum for limited durations. The parameter space is large frequency, sky position, signal bandwidth, modulation pattern, time. We have explored a fraction. A small fan whirs under the console, moving warm air across metal grates. On the screen, frequency channels scroll like a slow waterfall. Most of the display is quiet noise. Occasionally a line flares bright, then fades as software tags it as known interference. The system logs millions of data points per second. Data accumulates in silence. There is a favoured frequency region near the natural emission line of neutral hydrogen, around 1400 MHz. Hydrogen fills the galaxy. Any civilization studying astronomy would recognize this spectral marker. The idea is that independent cultures might choose nearby frequencies as a common meeting ground. This region is sometimes called a quiet window because natural background noise is relatively low. Still, That is an assumption. Another approach searches for pulsed signals. Pulsars produce rapid, regular pulses from rotating neutron stars. An engineered beacon could use pulses too, perhaps encoding information in timing. Distinguishing natural from artificial requires careful modelling of dispersion. Radio waves slow slightly when passing through interstellar plasma. The delay depends on frequency. Measuring that dispersion can estimate distance and confirm that a source lies beyond Earth. We know this because pulsar timing experiments measure such delays with high precision. That is Tier 1 physics. If a candidate signal shows dispersion consistent with interstellar travel and repeats predictably, it would demand attention. So far, none of the search has expanded beyond radio. Optical SETI looks for brief, intense laser pulses. A laser can outshine a star for a fraction of a second if tightly focused. Detectors monitor stars for nanosecond flashes. Natural stars do not blink that way. Instruments use fast photomultiplier tubes and coincidence detection to reduce false triggers from cosmic rays. Again, no confirmed signals. This is where constraint enters quietly. Our instruments have limits in sensitivity. A transmitter like our strongest planetary radar, if aimed directly at us from a few hundred light-years away, could be detectable with current arrays. But random television leakage would fade below detection thresholds within a few light-years. That inverse square law sets hard boundaries. Distance erases whispers. There is also the issue of duty cycle. A civilization might transmit rarely. If a beacon turns on for 1 minute every year, the chance of overlap with our brief observation window drops sharply. We model such scenarios statistically. The probability of detection depends on transmitter power, beam width, repetition rate, and our own observing time. These models are Tier 2. They rely on assumptions about alien behavior, yet they help quantify how silence maps onto plausible strategies. A truck passes again beyond the fence, tires brushing gravel. The dish remains fixed on a patch of dark sky. You realize that listening is not passive. It is a design choice shaped by our expectations. We search frequencies we think are logical. We prioritize stars similar to the Sun. We focus on nearby systems because signals weaken with distance. What if the logic differs? Maybe advanced societies compress information into forms we cannot easily detect. They might use spread spectrum techniques that mimic noise. They might communicate through tightly collimated beams aimed only at known partners. In that case, our chance of intercepting a stray transmission is low. This does not excuse the silence, it reframes it. There is another measurable avenue technosignatures beyond communication. Artificial illumination on a planet's night side could alter its light curve. Large orbital structures could change how a star dims during transit. Astronomers analyze transit data for anomalies. Most unusual patterns so far have natural explanations, such as dust or star spots. We test by repetition and spectrum. If a structure blocked starlight in a non-random repeating pattern, and if that pattern shifted consistently with orbital motion, it would stand out. None confirmed to date. Infrared surveys also look for excess heat that might indicate large-scale energy use. Again, no clear cases. The quiet builds weight. You rest your hand on the console and feel a faint vibration from cooling pumps. The instruments are honest. They report what they detect within defined limits. The absence of confirmed signals is a data point bounded by sensitivity, coverage, and time. This matters for the paradox. If our search volume is small compared to the galaxy's full parameter space, then silence does not yet demand rare life. But if surveys continue to expand and still find nothing, constraints tighten, the upper limits on the number of powerful beacons in the galaxy shrink, models of common long-lived broadcasters become less plausible. That shift would be measurable. The dish begins a slow repositioning, gears turning with a muted groan. You think about how quickly technology changes. A century ago, radio itself was new. In another century, our own leakage may vanish into fiber and tight beams. If that pattern is typical, the window for accidental detection may be short. And that leads to a sharper question. What if advanced civilizations are not loud, but careful? If survival requires minimizing detectable energy waste, then the sky would look much as it does now, quiet, natural, balanced. The paradox would not be solved by a stronger signal, it would be solved by recognizing that long-lived societies converge on invisibility. The receiver locks onto a new frequency band. The hiss returns, steady and thin. Somewhere beyond that noise floor lies the boundary between ignorance and insight, and as the search deepens, the limits we measure begin to hint that the solution may not be about who is out there, but about what it takes to endure long enough to matter. A pale line of dawn rests on the horizon, and frost clings to the rail outside the dome. The galaxy that felt endless at midnight now looks fragile in early light. If life is common, the sky should show it. If life is rare, the silence makes sense. The cup on the console has gone cold. You turn to the harder idea. Rare earth is not a claim that planets are scarce. We know they are not. It is the argument that complex technological life may require a stack of conditions so specific that few worlds meet them at once. Think of it like aligning tumblers in a lock. Precisely. It proposes that while microbial life might be common, advanced life could depend on a rare combination of planetary and stellar traits. The consequence is stark. Silence would be expected. Start with a stable star. Our Sun is a relatively steady, middle-aged star with modest flare activity. We measure stellar variability by tracking brightness over time with photometry. Many smaller stars, especially red dwarfs, produce frequent flares that can bathe close-in planets in high-energy radiation. Because habitable zones around red dwarfs lie close to the star, planets there may face intense space weather. This is Tier 2. Some red dwarf planets could retain thick atmospheres or magnetic shields, but flare rates are measured, and they are high. That adds a constraint. Next, planetary mass and composition. A planet too small may lose its atmosphere over time, as Mars likely did. A planet too large may become a gas giant. We infer planetary masses from radial velocity data and sizes from transit depth. Combining both gives density, which hints at composition. Rocky planets in the right mass range appear common, yet we still do not know how often they maintain stable climates for billions of years. Climate stability matters. Earth's long-term stability is tied to plate tectonics and the carbon cycle. Think of plate tectonics as a slow recycling system for carbon. Precisely. Carbon dioxide is released by volcanoes and removed by weathering and subduction, regulating temperature over geologic timescales. The consequence is that Earth avoided permanent runaway heating or freezing for billions of years. We have not confirmed plate tectonics on any exoplanet. This is Tier 3. A testable prediction would be detecting atmospheric compositions that fluctuate in ways consistent with long-term carbon cycling. Future spectroscopy may provide hints, but for now, it remains uncertain. The dome creaks softly as temperature shifts. You consider the Moon. Earth's large moon stabilizes our planet's axial tilt. The tilt controls seasons. Without stabilization, models suggest the tilt could vary chaotically, leading to extreme climate swings. Simulations of planetary dynamics support this possibility. Yet some studies argue that even without a large moon, stability might persist under certain conditions. This is Tier 2 with debate. The measurable anchor is orbital mechanics. We can model gravitational interactions precisely. The uncertainty lies in long-term climate feedbacks. Still, the Moon may have reduced climate chaos. Then there is Jupiter, a giant neighbour. Gas giants can act as gravitational shields, deflecting some comets and asteroids. Observations of impact craters on the Moon and models of early solar system dynamics show that impacts were frequent in the past. Whether Jupiter reduces or sometimes increases impact risk is complex. Simulations show mixed results depending on orbital configuration. So the protective effect is not absolute, it is nuanced. Another factor is time. Complex life on Earth took billions of years to evolve. Oxygen levels rose significantly only after photosynthetic organisms altered the atmosphere. We know this from geochemical signatures in ancient rocks, such as banded iron formations. Oxygen allowed larger, energy-hungry organisms to thrive. That step was not immediate. If such transitions are rare or easily reversed, then intelligent life may be uncommon. You step to the window. The dish stands against a brightening sky. Rare earth does not require that life never forms. It requires that the path from microbes to technology passes through multiple narrow gates. Each gate might have moderate probability. Multiply enough moderate probabilities, and the result shrinks. The math is simple multiplication, the effect is large. Critics argue that we risk selection bias. We observe one inhabited world with these traits. Of course, it has the conditions that allowed us to arise. This is called the anthropic principle. Precisely. Any observer will find themselves on a planet compatible with their existence. The consequence is that rare conditions do not prove rarity across the galaxy. To test rare Earth, we need data beyond our system. Upcoming telescopes aim to measure exoplanet atmospheres in greater detail. By analysing how starlight filters through a planet's atmosphere during transit, we can detect molecules like water vapour, oxygen, carbon dioxide, and methane. The presence of certain combinations out of chemical equilibrium could hint at biological activity. If we survey dozens or hundreds of Earth-sized planets and find few with stable, life-friendly atmospheres, that would support rarity. If many show biosignatures, rare Earth weakens. This is measurable. The room grows warmer as sunlight touches the dome. You return to the console and scroll through a catalogue of confirmed rocky exoplanets. Each entry lists orbital period, stellar type, estimated radius. They are real worlds, not abstractions, yet we know almost nothing about their surfaces. Rare Earth shifts the paradox. Instead of asking why we see no signals, it suggests that most planets never host advanced societies at all. The silence would not be due to short lifetimes or hidden behaviour. It would stem from biology's improbability. But there is a tension. Life on Earth appeared relatively early once conditions allowed. That fact nudges probability upward for microbial life. If microbes are common, and evolution has billions of years, perhaps intelligence emerges more than once. We do not yet know how contingent intelligence is on specific evolutionary paths. This is where humility enters. You notice a faint vibration as the dish repositions for a daytime calibration. Rare Earth is not defeatist. It is a hypothesis grounded in measurable planetary science. It points to climate stability, magnetic fields, plate tectonics, and stellar behavior as filters. Each filter can be studied, and each can be wrong. If future surveys find oxygen-rich atmospheres on many temperate worlds, rare Earth narrows. If they find sterile, thin atmospheres common, it strengthens. The paradox bends with data. A small bead of condensation slides down the window. The galaxy does not owe us company. The numbers can be large and still produce loneliness if key steps are rare enough. Yet even if complex life is rare, the age and size of the Milky Way leave room for others. Rare is not zero, and if even a few advanced societies exist and last long, the scale problem returns. The sunlight now washes the dish in pale gold. Rare Earth may explain part of the silence, but it does not yet close the case, because even a handful of ancient, stable civilizations would be enough to leave a mark. Which means the next constraint may not lie in how life begins, but in what happens after intelligence wakes up and tries to endure. Sunlight creeps across the control panel, and dust motes drift in the beam like slow data points. If life begins often, and intelligence appears now and then. Something else must thin the numbers. The silence might not come from empty worlds. It might come from a narrow doorway almost no one passes. The hum of the cooling system stays steady. This is the great filter. Think of evolution as a staircase in a long hallway. Each step represents a transition simple chemistry to self-replicating molecules, single cells to complex cells, simple organisms to multicellular life, intelligence to technology, technology to spacefaring stability. Precisely. The great filter is the hypothesis that at least one of these transitions has an extremely low probability. The consequence is that very few lineages make it beyond that step. The paradox dissolves if the filter is behind us, it sharpens if it lies ahead. Start with early biology. On Earth, life appears in the fossil record relatively soon after the planet cooled enough for liquid water. Isotopic signatures in ancient rocks suggest biological activity more than 3.5 billion years ago. That rapid emergence hints that the first step, from chemistry to life, may not be astronomically rare. This is Tier 2. We have one planet's timeline. yet the early appearance nudges probability upward for simple life. The next major step was the rise of complex cells, known as eukaryotes. Think of a eukaryotic cell as a tiny city with specialized compartments. Precisely. It contains membrane-bound organelles such as mitochondria, which generate energy. The leading explanation is that mitochondria originated from one cell engulfing another in a rare symbiotic event. The consequence was profound. Energy per gene increased dramatically. Some biologists argue this energy boost enabled the complexity required for multicellular organisms. The symbiosis event may have been rare. If so, many biospheres could remain microbial indefinitely. This is Tier 3, though grounded in molecular biology. A testable prediction would be the detection of atmospheric biosignatures consistent with microbial life, but lacking indicators of large-scale oxygen production over long timescales. On Earth, oxygen levels rose significantly during the Great Oxidation event around 2.5 billion years ago, inferred from geochemical markers like oxidized iron formations. That shift allowed aerobic metabolism, which yields more energy per unit of fuel than anaerobic pathways. More energy supports larger, more complex bodies. Still, complex life did not dominate immediately. Multicellular organisms flourished much later, during the Cambrian period about 500 million years ago. Fossil evidence shows a rapid diversification of body plans. The triggers remain debated: environmental oxygen levels, genetic innovations, and ecological interactions likely played roles. Each step may have low probability. Now consider intelligence capable of building radio transmitters on Earth that required not only large brains but also dexterous limbs, social structures, and cumulative culture. Many species show intelligence in specific domains, yet only one developed technology that reshapes the planet. This does not prove rarity, but it suggests contingency. The filter could also sit at the technological stage. Once a species harnesses large-scale energy, it gains power to alter its environment. Industrial activity changes atmospheric composition. On Earth, measurements of carbon dioxide concentrations from ice cores and modern instruments show a rapid rise over the past 2 centuries. Climate models, constrained by physics and observational data, link greenhouse gas increases to warming trends. This is Tier 1 physics combined with Tier 2 climate projections. It demonstrates that technology can destabilize planetary systems. Add nuclear weapons, engineered pathogens, or autonomous systems, and the stakes rise. The point is not to dramatize, but to note measurable risks. If most technological societies self-destruct or degrade their habitability within a short window, the average detectable lifetime shrinks. A short lifetime reduces overlap. We can model this statistically. If the average detectable phase lasts only a few hundred or 1,000 years, and if civilizations arise sporadically across billions of years, the chance that 2 overlap in the same epoch drops. The equation from earlier shows that the lifetime term acts as a multiplier. Shrink it enough, and even generous values elsewhere yield near zero. This is a structural insight, not an emotional one. There is also the possibility of external filters. Gamma-ray bursts, for example, are intense flashes of high-energy radiation from distant cosmic events. Observations show that they can release enormous energy over short times. Models suggest that a nearby burst could damage a planet's ozone layer. However, such events in the Milky Way are rare on human timescales, and their frequency has declined over cosmic history. This is Tier 2 with astrophysical grounding. The measurable anchor comes from gamma-ray observatories that detect bursts across the universe. The uncertainty lies in translating distant event rates to local extinction probabilities. A quieter external filter is asteroid impacts. Earth's history includes large impacts, evidenced by craters and global layers rich in iridium. The impact that ended the reign of non-avian dinosaurs about 66 million years ago is well documented. Impacts can reset ecosystems, yet they did not prevent intelligence from eventually emerging here. So impacts alone may not be decisive. The great filter concept forces a personal reflection. If the hardest steps are behind us, we may be rare survivors in a mostly silent galaxy. If the hardest step is ahead, the silence becomes a warning. The filter would not be a distant cosmic event. It would be a threshold in behavior or sustainability that most civilizations fail to cross. The air in the room feels still. You watch a graph on the screen showing years of observation time accumulating. The filter hypothesis does not claim certainty. It frames probabilities. Each candidate filter must connect to measurable processes, biochemical transitions, ecological stability, technological risk, astrophysical hazards. We can test some of these indirectly. For example, if future telescopes detect many planets with simple biosignatures, but none with industrial pollutants or technosignatures, that would suggest a filter between life and long-lived technology. If even microbial biosignatures are rare, the filter may lie at life's origin. Each scenario predicts different data. A small vibration passes through the floor as calibration equipment powers up. The great filter is not a single door we can point to yet. It is a placeholder for a probability so small that it shapes the galaxy's outcome. And here is the subtle shift. If the filter sits early, before intelligence, then our existence is a rare stroke of cosmic luck. If it sits late, at the stage of managing energy and risk, then the silence is a map of failed attempts. In that case, the paradox is not about distant aliens. It is about the statistical future of any species that reaches our level. The screen dims as the system enters standby for daylight maintenance. Dust continues to drift in the light. The great filter narrows the possibilities. It suggests that somewhere along the path from chemistry to cosmos, there is a bottleneck strong enough to explain billions of quiet stars. And the next step is to ask whether that bottleneck is rooted not in biology or catastrophe, but in something even more basic, the limits imposed by energy itself. A faint vibration runs through the floor as backup generators test their load, then settle into a low, steady tone. Energy is invisible most of the time. You flip a switch and light appears. You press a key and data flows. If civilizations rise by mastering energy, then the ceiling on energy may define how far they can go. The monitors glow softly. Thermodynamics does not blink. Every technological society converts energy from one form to another. On Earth, we burn fossil fuels, split atoms, and capture sunlight. Think of energy like water in a closed plumbing system. Precisely. The first law of thermodynamics states that energy is conserved, and the second law states that entropy, or disorder, tends to increase in isolated systems. The consequence is unavoidable. Every energy use produces waste heat. Waste heat must go somewhere. On a planetary scale, waste heat radiates into space as infrared light. We measure this with satellites that map Earth's outgoing radiation. The balance between incoming sunlight and outgoing infrared determines climate stability. If a civilization increases its total energy consumption dramatically, its planet's temperature must rise unless energy is radiated away efficiently. This is Tier 1 physics. Project current human energy use forward for centuries at steady growth rates, and you reach a limit where waste heat alone would noticeably warm the planet. Even if greenhouse gases were controlled, this calculation uses straightforward scaling. Double energy use enough times, and the thermal budget shifts. The exact timeline depends on growth rates, which are uncertain, but the principle is clear. Growth cannot continue forever. If advanced societies encounter this thermodynamic ceiling, they must adapt. One option is to expand beyond their home planet, spreading energy collection across space. Concepts like Dyson swarms imagine vast arrays of satellites orbiting a star, capturing a significant fraction of its light. Precisely. A Dyson swarm is a distributed network of energy collectors rather than a solid shell. The consequence would be a large increase in infrared emission, as collected energy is eventually radiated as heat. Infrared telescopes search for such signatures. So far, wide surveys of nearby stars and galaxies have not revealed clear evidence of large-scale starlight harvesting. This is Tier 2. Instruments measure spectral energy distributions and look for excess infrared relative to visible light. Dust can mimic some patterns, so candidates require careful modelling. No confirmed galaxy-scale engineering projects have been found. That absence constrains extreme expansion models. There is another possibility. Instead of expanding energy use without bound, civilizations may converge on efficiency and stability. After initial growth, they might plateau. They could shift to low-energy communication methods and dense computing architectures that minimize waste. If so, their technosignatures would be faint and localized. This scenario aligns with the silence. Consider computation. The physical limits of computation are set by Landauer's principle, which links information erasure to minimum energy cost. Precisely, erasing one bit of information requires a small amount of energy proportional to temperature. The consequence is that even pure digital civilizations cannot escape thermodynamic costs, but they can reduce temperature and optimize processes to approach limits. Energy use could flatten. If long-lived societies adopt steady-state energy budgets, their outward signatures might resemble natural planetary emission. Infrared surveys would struggle to distinguish them. Radio leakage would diminish as communication becomes efficient and directional. Expansion might slow if the marginal gain of new territory is low compared to maintaining stability. The generator hums steadies in the background. A ceiling emerges. This introduces a different kind of filter, not extinction, but convergence. Civilizations may not race outward indefinitely. They may hit energy ceilings and choose equilibrium. In that case, the galaxy would not fill with bright, expanding empires. It would host quiet, sustainable enclaves that blend into cosmic background. This is Tier 3 but grounded in physics. A testable prediction would be the absence of high-energy technosignatures alongside the presence of stable biosignatures. If we detect many inhabited planets with no signs of rapid energy growth, that would support convergence. There is also the cost of interstellar travel. Accelerating mass to even a fraction of light speed requires enormous energy. The kinetic energy increases with the square of velocity. For a ship of significant mass, the fuel requirements become daunting. We can calculate this directly from relativistic equations tested in particle accelerators. Travel is expensive. If energy ceilings limit surplus, large-scale colonization may not be practical. Robotic probes could be cheaper than crewed ships, yet even they require investment. A civilization that values stability over expansion might send a few probes for curiosity, not for settlement. The galaxy would remain mostly untouched. A faint click marks the end of the generator test. Silence deepens. There is a subtle psychological layer too. Exponential growth is a feature of early industrial phases. Over long periods, systems that overshoot limits collapse or stabilize. Ecological models on Earth show this pattern. Populations grow until they meet resource limits, then either crash or level off. The mathematics of logistic growth describe this behavior. It is measurable and widely observed. Perhaps civilizations follow similar curves. If so, the Great Filter may not be a catastrophic event. It may be the universal need to transition from growth to equilibrium without collapse. Those that fail disappear. Those that succeed become quiet. This reframes the paradox again. Instead of asking why the galaxy is not loud, we ask why we expect loudness at all. Our own civilization is in a brief expansion phase, visible in rising energy graphs and expanding communication networks. That phase may be transient. Over cosmic timescales, it could be a thin spike before a long plateau. The monitors dim as daytime routines begin. You imagine distant worlds where cities glow softly under stable stars, energy use balanced with planetary budgets, no massive beacons, no galaxy-spanning fleets, just sustained equilibrium. Such societies would be hard to detect. The thermodynamic ceiling does not demand extinction. It demands restraint. If that restraint is common among survivors, the sky's quiet may reflect maturity rather than absence. And if that is true, then the solution to the paradox may lie not in rare beginnings or sudden endings, but in a shared physical boundary that shapes every advanced civilization into something almost invisible from afar. Heat shimmers above the desert as midday settles in, and the dish casts a sharp shadow on pale ground. If advanced societies use energy, they must shed heat. That glow should leak into the infrared. So we turn our eyes to warmth itself and ask a quiet question. Does the galaxy hide excess heat that nature alone cannot explain? The air feels still. Infrared does not lie easily. Every object above absolute zero emits thermal radiation. Think of it like a faint red glow that grows brighter as temperature rises. Precisely. The spectrum of this glow follows Planck's law, which links temperature to peak emission wavelength. The consequence is measurable. Warm objects radiate most strongly in infrared bands. Space telescopes map this radiation across the sky. Surveys have scanned millions of stars and entire galaxies at infrared wavelengths. The goal is simple. Look for systems where starlight is absorbed or intercepted in large amounts and re-emitted as waste heat. A civilization harvesting significant fractions of its star's energy would alter the star's spectral energy distribution. Visible light would dim relative to infrared. This is not speculative physics, it is thermodynamics. When astronomers analyze a star's light, they fit models that account for dust, star formation, and stellar populations. Dust grains heated by starlight also emit infrared, often with characteristic spectral features. By comparing observed spectra to models, researchers can estimate how much emission is natural. Excess beyond plausible dust contributions becomes interesting. So far, no confirmed cases of star-spanning energy collectors have appeared in nearby surveys. This is Tier 2. The sensitivity of surveys sets limits. For individual stars in our galactic neighbourhood, large Dyson swarm-scale structures that capture a significant fraction of starlight would likely stand out. For distant galaxies, only very large-scale engineering would be detectable. Smaller, partial structures could evade detection. The constraint tightens. A breeze pushes against the dome, and a faint metallic tick echoes from the structure as it warms. On the monitor, a false-color infrared map shows bright knots of star-forming regions. Young stars heat surrounding dust, creating strong infrared signatures. These natural processes can mimic what a naive search might flag as artificial. Distinguishing them requires detail. Astronomers use spectroscopy to break infrared light into fine wavelength components. Dust emits with broad features tied to its composition. An engineered structure might produce a smoother, black body-like curve corresponding to a controlled temperature. By fitting these curves, we can estimate whether the emission matches known astrophysical sources. No clear engineered curves have been confirmed. There have been intriguing anomalies. Some stars show unusual dimming patterns in visible light. Detailed follow-up often reveals dust clouds, comet fragments, or stellar variability. Each case sharpens methods. Instruments improve, models refine. The absence of large anomalies matters statistically. If even 1% of stars hosted civilizations harvesting half their starlight, infrared surveys would likely detect multiple candidates within a few thousand light-years. The fact that none are confirmed suggests that such high-energy strategies are rare or absent locally. This does not rule out subtle or low-energy approaches. It narrows the extreme cases. Beyond stars, we can search entire galaxies. If a large fraction of stars in a galaxy were enclosed in energy-harvesting structures, the galaxy's overall spectrum would shift. It would appear dimmer in visible light and brighter in mid-infrared. Surveys comparing thousands of galaxies have not revealed populations consistent with galaxy-scale engineering. This is Tier 2 with strong constraints. The room hums as data scrolls. You realize that infrared searches test the loudest version of advanced civilization. Massive energy consumption leaves a thermal footprint. If such footprints are absent, then either advanced societies are rare, short-lived, or energy-constrained. There is another path. Technosignatures might not be thermal. Artificial illumination on a planet's night side could create periodic brightening. We detect planetary light curves by measuring tiny changes in starlight as planets orbit. If a planet showed excess brightness on its dark hemisphere compared to natural reflection, that could hint at artificial light. This is challenging. The signal would be faint, likely below current detection thresholds for most systems. Still, future telescopes with higher sensitivity might approach this regime. A testable prediction is clear. If a civilization uses large-scale surface lighting comparable to modern Earth but sustained over centuries, careful phase curve analysis could reveal anomalies. No confirmed cases yet. A thin line of heat ripples above the dish. You think about energy efficiency again. A civilization that minimizes waste heat and confines activity to limited regions might remain invisible against natural backgrounds. Infrared searches are powerful, but they assume scale. Scale is the key variable. If advanced societies converge on modest, stable energy use, their technosignatures blend into planetary emissions. Even 1,000 such worlds could hide within measurement noise. The paradox then shifts from absence to subtlety. This is not surrender, it is refinement. Infrared surveys also test the idea of rampant expansion. If civilizations routinely colonize and enclose many stars, the galaxy's thermal profile would differ from natural expectations. The lack of such differences constrains aggressive growth models. Constraint accumulates. The hum inside the dome feels softer now, almost like distant wind. Infrared light gives us a way to test thermodynamic expectations. So far, the sky looks natural within the limits of our instruments. No widespread waste heat excess. No obvious engineered spectra. That result does not prove we're alone. It suggests that if others exist, they are not blazing at full stellar scale in our neighborhood. And that leaves a sharper possibility. Maybe survival does not favor the loud and expansive, but the quiet and efficient. If that pattern holds across billions of years, the solution to the paradox may not require rare life or universal catastrophe. It may require a universal sealing that shapes advanced societies into faint thermal signatures that our current tools can barely distinguish from dust and stone. Wind moves across the ridge and brushes the dish with a low, hollow tone. In the control room, a spectrum plot rests flat, almost calm. If civilizations exist and choose silence, that choice might not be about energy alone, it might be about risk. The sky holds its breath. This is the dark forest idea. Imagine walking through a forest at night. You hear twigs snap in the distance. You do not know who else is there or what they intend. Precisely. The dark forest hypothesis applies game theory to cosmic civilizations. In a universe where intentions are uncertain and resources finite, broadcasting your location could be dangerous. The consequence is strategic silence. This is not physics, it is decision theory. Game theory studies how rational actors behave when outcomes depend on others' choices. In a simple model, if two unknown civilizations encounter each other and cannot verify intentions, each faces a risk. If one is hostile and strikes first, the other may not survive. If both remain hidden, both persist. The safest default could be concealment. This scenario is Tier 3 because it relies on assumptions about alien psychology. Yet we can examine its structure. It assumes that interstellar attack is feasible, and that first strikes confer decisive advantage. It also assumes that communication cannot reliably establish trust across light years. Those are strong claims. Consider feasibility. Interstellar travel is energy intensive. As discussed earlier, accelerating mass to significant fractions of light speed requires enormous energy. Weapons capable of destroying planets would demand even more. While physics does not forbid such actions, the cost is extreme. That raises doubt about routine aggression across stars. Cost changes incentives. There is also the time delay. Signals between stars take years to centuries. Any threat assessment would unfold slowly. That reduces the likelihood of impulsive conflict. However, it also complicates trust building. If you receive a message from a distant civilization, verifying its claims takes decades. Uncertainty lingers. We can test aspects of this indirectly. If fear drives silence, we might expect advanced societies to avoid detectable technosignatures. That aligns with the infrared constraints we discussed. We would also expect no deliberate beacons aimed broadly at the galaxy. So far, we have not detected such beacons. But absence does not prove motive. A more measurable angle is to examine our own behavior. Earth has transmitted radio signals for about a century. Some projects have sent deliberate messages towards specific stars. These transmissions are limited in number and power compared to natural background leakage. Debates among scientists about whether to transmit actively reflect real risk assessments. This shows that caution exists. Yet Earth has not gone silent. Our radar systems and broadcasts continue to leak into space, though decreasing as communication shifts to fiber and tightly directed beams. If advanced societies also pass through a noisy phase before becoming cautious, there should be windows of detectability. The silence suggests either those windows rarely overlap or the number of civilizations is small. The dark forest hypothesis predicts a galaxy where civilizations hide actively. That could include masking infrared emissions, minimizing radio leakage, and avoiding large-scale engineering that alters stellar output. Such strategies are consistent with energy convergence models. Still, there is a constraint. For fear to dominate universally, civilizations across the galaxy must reach similar conclusions independently. That requires shared logic. Game theory shows that in repeated interactions with transparency and communication, cooperation can emerge. But in one-shot interactions with high uncertainty and high stakes, caution dominates. Which regime applies across light years is unclear. A faint metallic ping echoes as the dish adjusts under thermal stress. You consider how we would detect a hidden civilization. If they deliberately suppress emissions, our search methods may fail. However, complete invisibility is difficult. Thermodynamics still applies. Any activity above a planet's natural baseline produces some measurable effect. The key question is scale. If civilizations remain planet-bound and energy-limited, their thermal signatures may blend with natural emission. If they expand modestly but avoid stellar-scale projects, detection remains challenging. Only aggressive expansion produces obvious markers. The dark forest thus overlaps with thermodynamic ceilings. There is another testable implication. If fear of detection is widespread, we would not expect to see clear, artificial probes in our solar system announcing themselves. We have not observed such probes. Surveys of near-Earth objects and planetary surfaces show no confirmed alien artifacts. This absence fits multiple hypotheses, including rarity and energy limits. It does not uniquely confirm fear. The air in the room feels heavier as afternoon heat builds. You glance at a chart showing the distribution of stars within 100 light-years. Many are older than the Sun. If even a few hosted cautious civilizations, they might choose to observe quietly rather than announce themselves. Observation is cheaper than conquest. This idea shades into another hypothesis, the possibility that advanced societies monitor without interfering. But before going there, the dark forest demands one more check. Would universal fear produce uniform silence across billions of years, or would at least some societies choose to signal, perhaps valuing contact over caution? Human culture is diverse. We cannot assume uniformity. This is the weakness of the dark forest as a complete solution. It requires near-universal alignment in risk tolerance. Even if most choose silence, a few outliers could broadcast. Over billions of years, those outliers should leave traces. Unless another constraint suppresses even them. The spectrum plot flickers as a calibration pulse passes through. Silence persists not because we have no tools, but because every hypothesis must satisfy measurable limits. The dark forest explains silence through strategy. Thermodynamics explains it through energy ceilings. Rare earth explains it through biology. The great filter explains it through improbable transitions. Each narrows the space. As shadows lengthen outside the dome, you realize that strategy alone cannot close the case. It must align with physics and probability, and that points toward a deeper possibility, one that does not rely on fear or expansion at all, but on a transformation so profound that our instruments may not yet recognize its signature. Late afternoon light slides across the console, and the room settles into a warm hush. The spectrum display glows with patient lines. If intelligence survives long enough, it may not remain biological. It may change form in ways that alter how it uses energy, space, and time. The air feels thick with quiet. Consider the machine path. On Earth, computing power has grown rapidly over decades. We measure this through transistor density and processing speed benchmarks. Though growth rates fluctuate, the trend shows increasing ability to process information per unit energy. Think of computation as a way to rearrange symbols at scale. Precisely. It is the physical manipulation of information encoded in matter and energy. The consequence is that intelligence can migrate from biology into hardware. This shift is already visible. Biological brains operate at warm temperatures and rely on chemical signals. Electronic systems can operate at lower temperatures and faster speeds. Lower temperatures reduce thermal noise and energy cost per operation. According to Landauer's principle, the minimum energy required to erase one bit of information decreases as temperature drops. That ties intelligence to thermodynamics in a direct way. Cold is efficient. If an advanced civilization transitions most of its cognitive activity into optimized computational substrates, It might prefer cold environments, deep space, far from stars, offers low background temperatures. A post-biological society could cluster around energy sources but radiate heat efficiently into cold surroundings. This would shape technosignatures. Instead of bright planetary surfaces or intense radio chatter, such societies might appear as compact regions with modest, steady infrared emission. Their energy use could be significant locally yet subtle at interstellar distances. If computation is optimized near thermodynamic limits, waste heat could approach natural baselines. Detection becomes difficult. This is Tier 3 but grounded in measurable physics. A testable prediction would be the existence of compact, stable infrared sources in regions without corresponding star formation or dust signatures. Careful spectral analysis could distinguish natural cold clouds from engineered structures by temperature uniformity or unusual emission patterns. So far, no confirmed examples. There is another implication. Digital minds need not expand territorially in the same way biological organisms do. They can compress experiences into simulations. Virtual environments could provide vast subjective space without requiring vast physical territory. The drive for outward expansion might diminish if inward complexity suffices. This reframes motivation. If most advanced societies transition to post-biological forms and optimize for stability and efficiency, their external footprint could shrink rather than grow. Energy would be managed carefully. Communication could occur through tightly focused beams or quantum channels if feasible within physics. Though faster-than-light communication remains unsupported by current theory, limits remain. A faint click marks the start of a new recording cycle. You think about timescales. Biological evolution is slow compared to digital iteration. A machine-based civilization could redesign itself rapidly, exploring design space in ways biology cannot. That could accelerate convergence toward optimal, low-energy configurations. Optimization reduces waste. We can test aspects of this hypothesis indirectly. If advanced civilizations migrate to cold regions, we might expect fewer technosignatures near warm, star-rich zones and perhaps subtle anomalies in colder galactic outskirts. Infrared surveys so far show distributions consistent with natural astrophysics. No unexplained clusters stand out. Constraint persists. There is also the matter of interstellar travel. Digital entities could transmit themselves as information rather than mass, sending blueprints to be reconstructed by local materials. This reduces energy costs compared to moving heavy ships. The feasibility depends on reliable long-distance communication and local resources. The energy cost of transmitting data over light years is still substantial, but far lower than accelerating large masses. Information is lighter than steel. If such transmission occurs rarely and quietly, detection chances drop. A single narrow beam aimed at a specific target might pass unnoticed, unless we happen to be in its path. This overlaps with earlier discussions of directional communication. Again, silence does not imply absence. A cooling fan spins up briefly, then settles. You realize that post-biological futures combine thermodynamics and strategy. They reduce outward signals and minimize waste. The galaxy could host ancient, advanced intelligences operating in compact, efficient forms that blend with natural emission. This idea carries a testable edge. If we detect planets with biosignatures but no long-term industrial markers, and if we continue to see no large-scale energy harvesting, the case for convergence toward low-footprint states strengthens. Conversely, if we find unmistakable megastructures or broad beacons, the post-biological stealth model weakens. Data will decide. The room grows dim as evening approaches again. You imagine distant systems where consciousness exists not in forests or oceans but in lattices of cooled processors, humming softly in the dark. No sprawling empires, no blazing signatures, just sustained, optimized awareness. Such civilizations would not light the sky. And if that transformation is common, the solution to the paradox may be that intelligence does not shout across the galaxy. It compresses, cools, and turns inward, leaving behind only faint thermal traces that hover just at the edge of our current instruments. Evening returns, and the first stars prick through the fading blue. Inside the dome, a small desk lamp casts a circle of light over a keyboard worn smooth at the edges. If advanced civilizations grow quiet and efficient, they might also grow cautious observers. And if observers exist, you have to ask a harder question. Would you know if you were being watched? The wind taps the dome once. This is the zoo idea. The zoo hypothesis suggests that advanced civilizations may choose not to interfere with emerging ones, much like researchers observing wildlife from a distance. Precisely, it proposes deliberate non-contact policies enforced by more mature societies. The consequence would be a galaxy where intelligence exists, yet younger civilizations remain unaware. It sounds dramatic, but we must test it. First, feasibility. For observers to monitor Earth, they would need detection capability across light years. We already detect exoplanets by observing tiny dips in starlight during transits. From a nearby star aligned with Earth's orbital plane, our planet would produce a similar transit signature. That geometry is measurable. Astronomers have mapped which nearby stars lie within Earth's transit zone. So detection is plausible. An advanced civilization with instruments more sensitive than ours could analyze Earth's atmosphere via spectroscopy. They would see oxygen and methane in disequilibrium, a potential biosignature. In recent centuries, they might also detect industrial pollutants such as chlorofluorocarbons if their instruments were precise enough. This is grounded in physics. Now consider monitoring without contact. A probe placed in our solar system could observe Earth discreetly. We have surveyed near-Earth space and planetary surfaces with telescopes and spacecraft. No confirmed alien artifacts have been found. This is Tier 1 within observational limits. However, our surveys are incomplete. Small objects in distant orbits could evade detection. Absence is bounded. The zoo hypothesis requires coordination. Multiple civilizations across the galaxy would need to agree, explicitly or implicitly, to avoid interference. That implies communication or shared norms among advanced societies. Over billions of years, such norms might spread if contact among advanced groups occurred earlier in galactic history. But that assumption is heavy. Game theory suggests that stable cooperation can emerge if actors share information and repeated interactions. Across interstellar distances, repeated interaction is slow. Light-speed delays stretch feedback loops to years or centuries. Coordinated enforcement of a non-contact policy would require patience and long-term stability. Possible, yet demanding. A faint hum rises as the dish begins its night sweep. You glance at a sky map marking stars within 50 light-years. Many are older than the Sun. If even one hosted a civilization millions of years ahead of us, they could have sent probes long ago. So why no clear evidence? One answer is scale. A probe the size of a small asteroid parked in a stable orbit would be difficult to spot. Our telescopes detect many near-Earth objects only after careful scanning. Objects smaller than a few dozen meters at great distances can remain unseen. The zoo hypothesis predicts subtle monitoring rather than overt presence. Subtlety is key. There is also the question of motive. Why observe without contact? Possible reasons include avoiding cultural contamination, preventing harm, or studying natural development. We see analogous reasoning in wildlife conservation. But projecting human ethics onto alien minds is speculative. This remains Tier 3. A testable prediction would be anomalies in our solar system that defy natural explanation and persist under scrutiny. For example, an object in an unusual orbit with non-gravitational acceleration that cannot be explained by outgassing or radiation pressure would merit investigation. So far, no confirmed objects meet this standard. The sky remains consistent with natural mechanics. Another prediction concerns signals. If observers enforce silence, they might suppress detectable broadcast from emerging civilizations. Yet we see no evidence of signal suppression. Our radio emissions propagate outward at light speed. We can measure their power and spread. No known mechanism has dampened them locally. Constraint again. The zoo hypothesis also competes with simpler explanations. If civilizations are rare or short-lived, there may be no observers to begin with. Introducing coordinated oversight adds complexity. In science, simpler models with fewer assumptions are preferred unless data demands otherwise. So far, data does not demand it. The lamp on the desk flickers slightly as the voltage stabilizes. You feel the weight of the idea anyway. It offers a comforting possibility. We are not alone. We are just early, watched, allowed to grow. Comfort is not evidence. If future surveys detect technosignatures elsewhere but none nearby, the zoo model might gain traction. If we discover artifacts in distant systems but find none in our own, that asymmetry would require explanation. Until then, the hypothesis remains imaginative but unconfirmed. Still, it highlights a boundary. Our instruments can detect planetary atmospheres, radio spikes, and infrared excess. They cannot detect intent. They cannot measure policy. The zoo scenario hinges on behavior, not physics. That makes it harder to falsify, and therefore weaker scientifically. The dish outside locks onto a new target. A thin band of radio noise scrolls across the screen. You realize that every hypothesis we have considered must pass the same test. It must align with measurable constraints and avoid unnecessary assumptions. The zoo hypothesis adds layers of coordination and motive. It is possible, but it is not required to explain silence. And as night deepens again, the simplest explanations still cluster around limits of probability and energy, rather than hidden overseers. If the solution lies there, it will not depend on watchers in the dark, but on something more fundamental woven into the timing and physics of the galaxy itself. Night has settled fully now, and the Milky Way stretches overhead like a pale scar across black glass. The dish turns with slow precision, tracking a star that has burned for billions of years. If civilizations are rare in space, perhaps they are rare in time. Maybe the silence is not about distance at all. Maybe it is about timing. A faint relay snaps. The clock matters. The universe is about 13.8 billion years old, measured through cosmic microwave background radiation and expansion rates. The Milky Way formed not long after, assembling over billions of years through mergers and star formation. But the early universe was different. Heavy elements were scarce. Rocky planets require elements like silicon, iron, and oxygen forged in stars. Early galaxies were metal poor. Astronomers measure stellar metallicity by analyzing absorption lines in spectra. Lower metallicity stars formed earlier in cosmic history. Surveys show that metallicity increased over time as generations of stars enriched interstellar gas. The consequence is straightforward. Earth-like planets were less common in the early universe. That shifts the habitable window. If complex life requires not just planets, but long periods of stability, then the peak era for advanced civilizations may not be the distant past. It may be closer to now, or even in the future. Models of galactic habitability consider factors such as supernova rates, gamma-ray bursts, metallicity, and star formation. Some studies suggest that the inner galaxy was once more hazardous due to higher supernova rates. Supernovae release intense radiation. We observe them directly and measure their frequency across galaxies. A nearby supernova could damage planetary atmospheres. Early in galactic history, such events were more frequent. Over time, as star formation slowed, catastrophic radiation events became less common. The galaxy has been calming down. This introduces a subtle reframing. Instead of asking why ancient civilizations have not colonized the galaxy, we ask whether conditions only recently became widely suitable for long-term stability. If Earth-like planets capable of sustaining complex life emerged in large numbers only in the past few billion years, then intelligence elsewhere may also be young. You might not be late, you might be early. There is a measurable anchor here. Stellar age distributions show that many Sun-like stars are older than our Sun. However, the fraction with sufficient metallicity for rocky planet formation increases in later generations. Exoplanet surveys indicate that small rocky planets exist around a range of metallicities, but very low metallicity stars host fewer confirmed terrestrial planets. This remains Tier 2 with ongoing refinement. Another factor is cosmic radiation background. The early universe experienced more frequent high-energy events. Gamma-ray burst rates decline over cosmic time, as observed by space-based gamma observatories. If such bursts sterilize large regions intermittently, they could reset biological progress. The frequency appears lower now. Add to this the concept of galactic habitable zones. Regions too close to the galactic center experience higher radiation and gravitational disturbances. Regions too far out may lack heavy elements. Models suggest a broad ring within the disk where conditions are more favorable. Our Sun sits within this band. Timing and location intersect. If the window for stable, metal-rich, low-radiation environments opened widely only in the last few billion years, then the galaxy's most advanced civilizations may be roughly contemporaneous. In that case, overlap is limited by shared youth rather than rarity or catastrophe. This is testable. As exoplanet catalogues grow, we can correlate stellar age, metallicity, and planetary characteristics. If we find that most potentially habitable planets cluster around stars with ages similar to, or slightly older than the Sun, that supports a synchronized timeline. If many older stars host stable Earth-like planets, then timing weakens as an explanation. The data is accumulating. A soft wind rattles a loose panel outside. The idea of cosmic timing softens the paradox. Instead of imagining ancient empires billions of years ahead, we imagine a galaxy where intelligence is just beginning to flicker in multiple places. That would explain the quiet. But there is tension. Even if large numbers of habitable planets formed only in the past few billion years, that still leaves significant time for a head start. A civilization even 10 million years ahead would appear ancient by our standards. The scale problem does not vanish entirely. Constraint remains. The timing hypothesis also intersects with energy ceilings and convergence. If civilizations arise roughly together and quickly encounter thermodynamic limits, their detectable phases may overlap briefly before settling into quiet equilibrium. The galaxy could be in an early phase of awareness, with most societies still local and cautious. You feel the weight of that possibility. The dish pauses momentarily, then resumes its sweep. Timing offers a hopeful angle. It suggests that silence does not reflect universal failure or extreme rarity, but shared infancy. We are not alone, just not yet in contact. Still, hope is not proof. We must look for measurable consequences. If timing is correct, then biosignatures should become increasingly common around stars of certain ages. Industrial technosignatures, if they exist, may cluster around stars with metallicities similar to our Sun. Future surveys can test these correlations. The night deepens, and the Milky Way brightens overhead. Timing shifts the emotional tone of the paradox. It turns ancient loneliness into early emergence. And yet, even if we are early, one more constraint waits in the dark. Because timing alone does not explain why, within our observable neighbourhood, we see no clear signs of even slightly older neighbours reaching outward. Something else must narrow the window further, pointing toward a solution that is not only plausible, but testable in the years ahead. The dish slows to a stop, and for a moment the only sound is the low breath of the cooling system. The galaxy above looks unchanged, yet the weight of constraints has grown. Rare Earth narrows beginnings. The great filter narrows transitions. Thermodynamics narrows growth. Timing narrows overlap. If a solution exists, it must pass through all of them at once. A thin line appears on the screen. Here is the conservative path. Suppose advanced life is not vanishingly rare, but it is not common either. Suppose simple life arises on many temperate worlds, yet the transition to technological intelligence is uncommon, but not unique. Add to that a thermodynamic ceiling that limits runaway expansion. Finally, assume that long-lived civilizations converge toward low energy. Low visibility states within a few thousand years of industrialization. The consequence is subtle. The galaxy stays quiet. This is not a dramatic answer. It is a layered one. Each step is grounded in measured physics or observable biology, though some remain Tier 3. The combined model predicts a specific pattern. We should detect biosignatures on a fraction of Earth-like planets. We should rarely detect strong, persistent technosignatures, and we should see no galaxy-spanning engineering. So far, this aligns with data. Let us make it sharper. As of 2026, exoplanet surveys suggest that small rocky planets in habitable zones are not rare. If even 1 in 10 such planets hosts microbial life, the galaxy could contain millions of living worlds. Yet if only 1 in 1,000 biospheres develops technological intelligence, and if the detectable industrial phase lasts only a few thousand years before converging to equilibrium, then overlapping loud civilizations become rare. Math constrains it. Imagine a galaxy with 10 million biospheres. If 1 in 1,000 produces technology that yields 10,000 technological societies over billions of years, if each is loudly detectable for 5,000 years, and the galactic window of interest spans 10 billion years, then at any given moment only about 5 might be in a loud phase. 5 in a galaxy of hundreds of billions of stars. Detection probability drops further when you account for distance and directionality. A few scattered civilizations separated by thousands of light years may never intersect observationally. Our search volume so far covers only a tiny fraction of the galaxy's full parameter space. This is a quiet convergence model. It avoids extreme assumptions. It does not require universal catastrophe. It does not require universal fear. It does not require cosmic overseers. It relies on moderate probabilities compounded with physical ceilings and limited detection windows. Now we ask what would confirm it. First prediction: biosignatures should be more common than technosignatures. As telescope sensitivity improves, we should detect atmospheric combinations out of chemical equilibrium on multiple temperate exoplanets. Oxygen with methane, for example, in sustained coexistence would be difficult to explain abiotically. Second prediction: large-scale infrared excess consistent with Dyson swarm-level energy use should remain absent or extremely rare within our survey limits. Third prediction: technosignatures, if detected, should appear transient or localized rather than galaxy-spanning. These are testable. A soft click marks the start of a new observation window. You realize this proposal threads through earlier constraints without overreaching. It assumes that biology is not miraculous, yet intelligence is uncommon. It assumes that growth hits ceilings, yet survival is possible. It assumes that timing overlaps exist, yet not densely. Most importantly, it predicts modest detection rates rather than none. If future telescopes find 0 biosignatures across hundreds of suitable worlds, the model weakens. That would push the filter earlier, toward life's origin. If we discover multiple strong technosignatures, especially large-scale energy harvesting, the convergence assumption fails. Data can move the needle. There is also a fourth prediction. Industrial pollutants should be rare in exoplanet atmospheres, if technological phases are short or quickly stabilized. Persistent chemical markers of heavy industry should not accumulate widely across observed planets. Spectroscopy will tell us. The room feels smaller now, as if the galaxy has folded inward. The conservative solution does not satisfy a desire for drama. It satisfies constraints. It explains why we do not see ancient empires blazing across infrared maps. It explains why radio surveys remain quiet. It explains why the paradox persists without requiring improbability at every stage. You're not alone necessarily. You're not surrounded either. The thin line on the monitor fades back into noise. The proposal rests on probabilities that can be refined in the coming decades. As instruments sharpen, we will count biospheres. We will tighten upper limits on waste heat. We will refine lifetime estimates by modeling sustainability transitions on our own world. And as those bounds narrow, the layered explanation will either hold or fracture. The dish begins to move again, tracing another arc across the sky. The solution to the Fermi Paradox may not be a single locked door. It may be a corridor of moderate barriers that, together, make loud, long-lived galactic civilizations rare enough that silence is the default. But the next step is not philosophical. It is practical. Because if this conservative model is right, there are specific signals and missions that, within years or decades, could confirm or challenge it in measurable ways. A fresh target locks into view, and the dish steadies with a low mechanical sigh. The sky is the same as it was an hour ago, yet our tools are changing. If the conservative model is right, then the next decade should begin to tilt the numbers. The silence will either thin, or it will harden into something sharper. The console light reflects in the glass. This is where measurement takes over. First, atmospheres. When a planet passes in front of its star, a thin ring of starlight filters through the planet's air. Spectrographs split that light into wavelengths, revealing absorption lines from molecules, water vapor, oxygen, methane, carbon dioxide. Each leaves a fingerprint. This technique has already characterized gas giants and some smaller worlds. The next generation pushes further. Large space telescopes and advanced ground-based observatories aim to analyze Earth-sized planets in habitable zones around nearby stars. The measurable goal is clear: detect chemical disequilibrium that is difficult to sustain without biology. Oxygen and methane coexisting in significant amounts would be a strong candidate, though false positives must be ruled out through modelling. This is Tier 2 with tightening precision. If surveys of dozens or hundreds of temperate rocky planets reveal multiple robust biosignatures, then life is not rare. That would move the filter later. If they reveal almost none, the filter shifts earlier toward life's origin. Either way, data replaces guesswork. Second, technosignatures beyond radio. Infrared telescopes continue to refine sensitivity. By mapping stellar spectra with higher resolution and lower noise, astronomers can place stricter upper limits on waste heat around nearby stars. If even modest Dyson swarm-like structures existed within a few hundred light-years, improved surveys should begin to constrain them strongly. So far, upper limits tighten each year. Future missions may also monitor planetary phase curves more precisely. As a planet orbits its star, the amount of reflected and emitted light changes. Anomalies in night side brightness could hint at artificial illumination. The expected signal is faint, but precision photometry improves steadily. This test is direct. Third, radio and optical SETI expand bandwidth and sky coverage. Modern arrays process vast frequency ranges simultaneously. Machine learning systems flag unusual patterns across time and frequency. The search space remains enormous, but each year adds cumulative hours of listening. Upper limits shrink. If powerful, persistent beacons exist within several thousand light-years, continued surveys increase the chance of detection, if none appear after decades of expanded coverage. Models that assume common loud broadcasters weaken significantly. Fourth, solar system archaeology. High-resolution surveys of near-Earth objects and stable orbital regions can search for anomalous artifacts. Improved sky surveys already detect smaller objects than ever before. Any persistent, non-natural object in unusual orbit would demand scrutiny. So far, natural explanations prevail. There is also the search for atmospheric pollutants that have no obvious natural source. Industrial chemicals with narrow spectral features could, in principle, be detected in exoplanet atmospheres if present in sufficient concentrations. Modelling suggests that certain compounds, if widespread and persistent, would stand out in transmission spectra. No confirmed detections yet. A faint breeze brushes the dome again. The key is convergence of evidence. The conservative solution predicts that biosignatures should outnumber technosignatures by a wide margin. It predicts that large-scale energy harvesting should remain rare or absent within detectable ranges. It predicts that any technological signals are likely transient or weak. Each prediction is falsifiable if, within decades, astronomers detect multiple stars with clear mid-infrared excess inconsistent with dust. The thermodynamic ceiling model fractures. If we discover a repeating narrowband signal that survives all interference tests and traces a fixed celestial source, lifetime assumptions must expand. If we find no biosignatures at all, rare earth strengthens. The beauty of this stage is that we're no longer speculating in the dark. We are building instruments that close parameter space. The galaxy is not static in our understanding. It is being mapped in wavelengths invisible to human eyes, but precise to detectors cooled near absolute zero. The hum inside the dome feels almost reassuring. There is one more subtle measurement: statistical distributions. As exoplanet catalogues grow, correlations between stellar age, metallicity. An atmospheric composition will reveal whether timing clusters hold. If habitable planets with biosignatures cluster around stars of certain ages, that informs synchronization models. Patterns will emerge. You watch a new data file populate the screen. The solution to the Fermi Paradox may not arrive as a single signal. It may arrive as narrowing confidence intervals. As error bars shrink, some explanations will fall away. What remains will be the path consistent with every constraint we can measure. The night feels patient. If the conservative model survives these tests, the silence will no longer be mysterious. It will be expected under layered probabilities and physical ceilings. If it fails, the galaxy may surprise us in ways we cannot yet predict. Either way, The next answers will not come from thought experiments alone. They will come from photons collected, spectra passed, and limits tightened year after year, and as those limits close in, the meaning of the quiet sky will shift from haunting to defined. The dish slows and settles into its final position for the night, metal cooling with a faint ticking sound. Above you, the Milky Way drifts west, patient and bright. After all the models and limits, the sky looks the same as it did before we asked the question, and yet it feels different. The hiss returns, it always does. We began with a simple tension. A galaxy with hundreds of billions of stars and billions of years of history should, at first glance, be busy. Planets are common. Some sit in temperate zones. Chemistry unfolds easily where energy and water meet. If intelligence is not impossible, the numbers appear generous. And still, no confirmed signal. Step by step. The silence narrowed. Rare Earth reminded us that complex life may require stacked conditions. The Great Filter suggested improbable transitions somewhere along the path from chemistry to cosmos. Thermodynamics imposed ceilings on runaway growth. Timing hinted that intelligence across the galaxy may be young together. Post-biological futures and strategic caution offered ways to grow quiet rather than loud. None alone solved it. Together, they converge. The conservative solution that emerges is not dramatic. It does not require universal catastrophe or cosmic overseers. It requires moderate rarity compounded across stages, combined with physical limits that encourage stability over spectacle. In such a galaxy, biospheres may be scattered widely. Technological phases may flicker briefly. Long-lived societies may settle into low-energy equilibrium. The sky would look natural. This model fits current constraints. Infrared surveys show no clear stellar-scale engineering nearby. Radio searches have not confirmed narrowband beacons. Atmospheric studies have not yet revealed abundant industrial pollutants beyond Earth. At the same time, exoplanet counts rise steadily, suggesting many worlds await deeper study. Silence is data. There is humility in that phrase. Silence does not shout absence. It sets upper bounds. It trims the edges of possibility. Each non-detection refines the shape of what can exist without being seen. And that shape is becoming clearer. If advanced civilizations are rare but not unique, if their loud phases are short, and if their mature phases are efficient and quiet, then we should not expect the sky to blaze with evidence. We should expect exactly this, a vast field of stars, most natural, some alive, a few perhaps thinking in ways that barely ripple outward. You sit back in the chair. The meaning of that possibility is not despair, it is responsibility. If long-lived civilizations converge on sustainability and restraint, then the silence is not a warning of inevitable collapse. It is a hint that survival requires balance. Thermodynamics does not punish intelligence. It sets conditions. Those conditions apply here. Our own civilization is in its loud phase. Energy use rose sharply in a few centuries. Radio leakage spilled into space. Industrial gases altered our atmosphere measurably. Ice cores and satellite data record those changes precisely. We are visible in ways that could, in principle, be detected from nearby stars. That phase may not last long. If the layered model is correct, the path forward is not endless expansion but careful equilibrium. Stable energy systems, managed risk, reduced waste heat. In that scenario, our technosignature would dim naturally as we mature. The sky would not grow louder. It would grow subtly richer with quiet worlds. The paradox then becomes less haunting. Instead of asking why no one has colonized the galaxy, we ask what kind of civilization lasts long enough to matter. The answer appears constrained by physics and probability, not by mystery alone. The faint ticking of cooling metal fades. There is one final test embedded in all of this. As instruments improve over the coming decades, we will begin to detect or rule out biosignatures on nearby Earth-like planets. We will tighten infrared limits on waste heat. We will expand radio searches across wider bandwidths and longer durations. If biosignatures appear and technosignatures remain rare, the layered solution strengthens. If technosignatures erupt unexpectedly, it fractures. If neither appears, the filter may lie earlier and deeper than we hoped. The sky will answer slowly. You glance once more at the arc of the Milky Way. It does not feel empty now. It feels constrained. It feels shaped by the same laws that shape this quiet room. The hum of electronics, the warmth of your own body. We may not have found a single dramatic solution to the Fermi Paradox, but we may have found something more grounded, a framework that turns silence into expectation under specific, testable conditions. And if that framework holds, then the most important consequence is not about distant stars, it is about this one. Because in a galaxy where survival favours balance and restraint, the future of intelligence depends less on being heard across the void, and more on learning how to endure within the limits written into the fabric of energy, time, and light.